fall. Then as we get to about half the radius of the Earth, we enter the solid mantle. This is a silicate rock. Most of the Earth is made out of mantle. About 70% of the Earth is the mantle. This is inaccessible except by seismic waves, although once in a while a piece of the mantle gets shoved up on top of the crust and we can look at it. Then the part of the Earth that everybody's familiar with is the crust, and that's what we live on. That's where we get our resources. That's what we mine. But it's only a very thin scum on top of the mantle.
Even today, more than 4.5 billion years after the formation of the Earth, there are two layers of the planet that remain molten or partially molten. The uppermost mantle beneath the crust has now solidified, but a zone beneath it, several hundred kilometers thick, approaches the temperature of melting.
Okay, keep your notes, okay?
This is where the lava in most oceanic volcanoes comes from.
You can use some of my notes, okay? You won't have
The outer part of the Earth's core is also still completely molten, but the inner core, although even hotter, remains solid.
Okay.
This is due to the fact that when rock melts, it expands.
In the next week, I'll team you up with
But at the center of the Earth, the pressure of the 5,000 kilometers of overlying rock is so enormous that no expansion is possible. And as a result, the superheated iron cannot turn liquid. The great amount of heat still present in the Earth is demonstrated by active volcanoes. The volcanoes of today are an awesome spectacle. But more feverish convulsions affected this planet when the Earth was young.
In the present Earth, the amount of liquid rock is really quite small at any time. But in the early Earth, a big fraction of the volume would have been molten. So we imagine that the very earliest Earth had an extremely high level of volcanic activity. When this volcanic activity takes place, gases which are dissolved within the liquid rock are expelled, put into the Earth's atmosphere. And in this way, we can imagine that the early atmosphere of the Earth was built up by volcanic activity.
Our early atmosphere was something you and I would not want to breathe. Well, we wouldn't even today want to go breathe the air that comes, or the gases that come out of volcanoes. It's rich in sulfur, carbon monoxide, carbon dioxide, any of the same things that are emitted from the exhaust pipes of cars are coming out of volcanoes. They did then, they do today. It's a very acidic, very toxic gas. So our early atmosphere was pretty hazardous.
Volcanic activity also released vast amounts of water vapor. Many geologists argue that this condensed to form the world's oceans. Recent work, however, suggests that factors other than volcanism may also have played a role.
Another very interesting possibility is that the water came in comets, in bodies that formed in the far reaches of the solar system and were scattered into Earth-crossing orbits. We now see, of course, comets that cross the Earth's orbit, like Halley's Comet, and very rarely objects like this even hit the present Earth. But in the early history of the solar system, these collisions would have been more frequent. And the amount of water on the Earth, although we might think of it as being large because we live on the surface of the Earth, is actually quite small compared to the total mass of the Earth. And so you don't need a very large number of comets to explain all of the water that we see in the Earth's oceans.
Earth's distance from the sun and the presence of an atmosphere which kept surface temperatures warm allowed water to collect in a liquid state, submerging the young planet's raw basaltic lowlands. No other planet combines all the factors required for the existence of a watery ocean. An ocean may also explain the presence of life on Earth, for liquid water is an essential ingredient of biological reactions. The oceans played a further role in nurturing life, however, for Earth's early atmosphere was probably full of deadly solar radiation. Water would have screened out such radiation, enabling the fragile process of life's origin and early development to take place.
The most significant difference between Earth and the other planets in our solar system is that Earth has the conditions to support life as we know it. The abundance of water on Earth was critical to the origin of life. water also helped moderate the temperature of the planet's surface to a range which enabled life to evolve. Oxygen gas, however, was not part of this primitive atmosphere. It wasn't until the development of primitive algae about 1.8 billion years ago that free oxygen became an important part of the atmosphere of the Earth. This paved the way for the development of more complex life forms.
Come on.
Primitive blue-green algae, or cyanobacteria, survive by taking one of the most abundant gases released by volcanoes, carbon dioxide, and combining it with water in the presence of sunlight. The result is carbohydrates used for food and an important waste product called oxygen. So, through time, early life forms helped to change the carbon dioxide-rich atmosphere to one rich in oxygen, thus permitting the